I'm Kristofer Baxter. It's very nice to be here with you all today. I'm a software engineer here at Google, and I am the TL for the special ops team that works on AMP, specifically working on AMP script, which we're going to talk about today, as well as initiatives around reducing the size of the AMP runtime library. So, to be clear, AMP does love JavaScript. It may seem a little strange because not a lot of JavaScript exists within author code on AMP documents, but the entire AMP library is built using JavaScript. We think JavaScript's a very powerful, dynamic language that allows you to accomplish a lot, and it is the backbone of the way that the web works. We'd like to let developers use more JavaScript in their applications, but remember our trade off conversation earlier. We don't want to impact user experience. So it's been hard for us to find a solution that makes this work without significant impact on how people use AMP documents. It's a complex story, and we're going to walk through a little bit about how we've gone about trying to solve it over the course of the last few months. First, a few definitions. I apologize for the all text slides. I promise we'll have a bit more imagery soon. Concurrency is a very technical word, but it really means that you are allowing multiple parts of a computer program to run at the same time. Concurrency is a very core concept to allowing JavaScript in AMP, and it's important to understand that it means a very specific thing in computer science. However, for our definition, we just mean you can run multiple things simultaneously. That's it. If your phone has more than one core, which it does, or you have more than one computer, and the cloud definitely has more than one computer, then you can accomplish a lot more things simultaneously and a lot quicker. However, like most things in computer science, it comes at a trade-off. And that trade-off here is complexity. It is far more complex to handle concurrent operations than it is to handle them in serial order. So again, threads, programs that run on a computer. You can have several threads that are running at any given time on your machine because you have a CPU that's capable of processing many at the same time. Even a single CPU is capable of processing multiple threads simultaneously through shared work across that core. And single-threaded is a very specific concept when it comes to computer science, and for us, a very important concept for the browser. What this means, it's an application with a single thread. And what happens in these specific applications is that what you run in that thread is the only thing that runs at that current time. Traditionally, web browsers have only a single thread, just one. Now, this is changing over time. However, it remains the right mental model to think of when building web applications. We call that thread the main thread. JavaScript runs on that thread, and while JavaScript runs, there's nothing much else that the browser can accomplish. Your browser is pretty much locked running your JavaScript. There are exceptions, of course, but this is a very simple mental model that encapsulates the vast majority of JavaScript on the web. So what does this mean? Well, we talk about runtime performance a lot across the web, and we are trying to maintain a very constant, steady frame rate, 60 frames per second. Here in a single second of time, what that really means is a bunch of time slices, 16 milliseconds apiece. Each one of these are individual frames that operations need to occur within. Now, if you think about normally going to the movie theater, you're running around 24 frames per second, and you don't notice as a human that it's a slower frame rate. The reason for that is that it's a steady, constant frame rate. But applications on the web, while shooting for the 60 frames per second target, tend to unintentionally cause problems. Let's say, for instance, one or two of those frames misses its target window. What happens in this case is we get an irregular frame rate, and we call this jank. So you have 16 milliseconds to update the screen, right? Well, that's not true, unfortunately, because there's a lot more that has to happen within that time. There's you, then there's layout, style, recalc, paint, composite, and eventually we actually have to flip the pixels on the screen itself. That's a lot of stuff that needs to happen at 16 millisecond cycles over and over and over and consistently. So let's break that time down a little bit. If we look at the main thread in that 16 millisecond time slice, we need to kind of split it in half. Now, this is not a set in stone rule, but it's a pretty clear and good way of measuring how to work in this kind of system. In 8 milliseconds, your JavaScript runs. And the remaining 8 milliseconds of a frame, the browser responds to the changes that you've given it for that frame. Now, this doesn't mean that the browser will always take 8 milliseconds to process whatever changes you've given it. Sometimes it could take 2, sometimes it could take 10. But generally, think of the time in a frame as split in half. So that really means we're down to 8 milliseconds to run all of our JavaScript per frame. Let's hope our JavaScript isn't too expensive. And guess what? Often it is. Here's an example. We've got a click event that comes in, and we're using a fairly modern common framework. I won't have to name which one. You'll probably figure it out as we go. Your JavaScript is running on the main thread, and we need to process that specific event. So this means we have an event listener attached to that click event. Next, we need to determine some new state. Many JavaScript frameworks have the concept of mutable state or immutable separate state per action. Here, we're going to determine new state based off of previous state plus this click interaction that occurred. The next step is for us to respond to that state change. So popular frameworks may do virtual DOM diffing at this time, or they may have more hardwired direction between the change that's occurring and the actual DOM updates they want to process. And the last stage is to actually issue those DOM updates. Typically, these are synchronous APIs that you fire in rapid succession per frame. We made it. Congratulations. We have a buttery smooth application, never missing a single frame. But that's not what happens in the real world. What happens in the real world is that state change takes 2 milliseconds longer, or that device you're running on is 10% slower than you expected it to be. And suddenly, the amount of time that we expected, 8 milliseconds, is really 10. We have unintentionally moved that frame budget out by 2 milliseconds in our critical path. Not a big deal though, right? Now we're at 10 milliseconds for our code, but the browser still needs that 8 milliseconds. So we've busted our frame budget. We've gone from 16 milliseconds to 18 milliseconds in this example. And unfortunately, we've just introduced more jank. This one frame is unstable compared to the remaining frames around it. The human will be able to perceive this frame being off comparatively. It is common to exceed your budget. It happens to all of us in every single web application across the planet. Do not feel terribly bad about this. It is very hard to get this right. And it is something that the entire industry is working to make better. And there's a lot of reasons for this, but specifically we're going to talk about a few. So which one in particular is the most important to AMP? Well, the main problem for us is that not all mobile devices are created equal. Devices will have high CPU and terrible networks, or amazing networks and slow, clogged CPUs that are running other things. This difference in the capabilities of devices at a specific invocation time means that you don't really know how fast an app is running in the real world without metrics. So let's talk about metrics. Not many people actually break down the metrics in a consumable way, and we hope that this next few slides will help to help convince you why you need to pay more attention to the runtime performance of the low-end devices. So let's pretend we're walking into a store today or in 2011 and we're purchasing a brand new device. When we do this, we're going to break these devices down into price segments. So in our 15th percentile today, walking into a store, would be roughly American $80. So brand new device, retail $80, you walk in, you walk out with the device. The second category that we're going to look at is the 75th percentile. So this is where you're spending roughly $600. That's a huge jump step in performance, but also in price. And lastly, let's look at the third category, which is roughly the 90th percentile. Now you're willing to spend $1,000 or more. Devices in this category can be $1,500 for one device. That's a lot of money. And not many people actually buy these comparatively to what we imagine, because these are the devices that most of us use here in this audience. What does performance look like on these devices? So what I've done here is I've charted out performance of devices within those segments across time. So if you bought a device in 2013 that was in that 15th percentile, this is its single core performance. If you bought a device in that same 15th percentile in 2018, this is its performance. Not a lot of improvement, roughly 3 to 5% over 5 years in this segment. And the reason for this is really clear. These devices are getting cheaper, not faster. You can buy that 15th percentile device for $80 now, whereas a few years ago it was more like $100 or $120. The next category looks a little bit better. Here we see Moore's Law in action. You're even starting to see specialized hardware on these devices for unique operations. The Pixel ships, for instance, with machine learning hardware embedded on the device. Performance here is significantly improving, but it's not what everyone has in their pockets. And we do need to talk about the elephant in the room, which is the A series of processors, which are outstripping Moore's Law by an unbelievable amount. These things are like the Cadillacs of CPUs on a mobile phone. They're unbelievable. The amount of engineering resources and RAM on each one of these, or cache on each one of these devices, is much higher than anything else in the industry. This creates a very big problem. The problem this creates is a performance gap. What happens is we pull out our devices in our pockets and we test things that we build using those devices. I happen to have an iPhone in my pocket that is at the very top of that curve. When I test things that I build using that device, it looks buttery smooth. There's no jank. Everything is great. But if I take that same application and I run it against a lower end device or something on that 15th percentile curve, I get a very different picture. I get something that's nearly unusable. The high performance capabilities of these devices at the top end are masking the true issues in our code. There has to be some silver light at the end of the tunnel, or whatever the right analogy is, right? Well, that is multi-core performance, luckily. So if we take that same 15th percentile, you can see that there is some opportunity for improvement. It's not significantly high, but it's enough. We're able to take a few frames where we would have missed our budget beforehand and hopefully make them fit. It can't be that bad, right? It just can't be that bad. That's too far of a delta. It's inconceivable how slow these devices are compared to the high end. Well, I'm going to make you watch a video, and I apologize, it's a little long, but it's very important. Here on the left, we have the 90th percentile device, and on the right, we have something in the 15th percentile. This is running a very specific benchmark called Aries 6. Aries 6 is a nice benchmark to prove runtime performance of these devices. There's no loading of JavaScript. There's no network access. Everything's running locally on the device. It's using newer JavaScript techniques and using ES 2015 plus features. One of these tests, as crazy as it sounds, runs a Babel transformation on a large code base. Now, that's probably not what you're doing in your apps, but Babel is written using rather new ES 2015 features. It's a great stress test of what's possible in runtime performance. Our iPhone is just about to finish the entire battery of tests 6 times over at roughly 48 seconds. And now the device on the right is still working on the first of 6 passes. iPhone finishes 6 passes in 48 seconds. Device on the right has not finished one in 2 minutes and 40 seconds. And we're still going to have to wait. Now, I've sped this up a lot. I think we're at 16 times speed now, and I think I continue to speed it up. But this is what the difference is in runtime performance on these devices in a real-world-like scenario. This is what people have in their pockets. Great. We got through 1 of 6 runs on the low-end device in 5 minutes and 19 seconds, compared to 6 passes in 48 seconds. We need some concurrency in our JavaScript. As an industry, we need this badly. Mobile devices on the low end can take advantage of it much better than what we're doing today. So I'm really, really, really pleased to introduce a brand new API called Web Workers. They're fantastic. You're going to love them. And the great part about it is that they actually were introduced all the way back in 2009. So I don't know how many of you guys remember Ajaxian. It's a really great blog. And if you see something that is on Ajaxian, there's a very good chance it's gone away by now. Not that it doesn't exist everywhere, but that it's gone away. Web workers have been here and they've been waiting for us to use them for years. But they're hard to use, and that's why we haven't used them. So what are workers? Workers are a way for us to do multi-threading in JavaScript within web browsers. They share no state with one another or the main thread. They have access to a very limited number of APIs. And most importantly, for web developers, they have no access to the DOM. You cannot modify the DOM of the parent page within a web worker. This restriction has made them hard to use for many cases. Let's talk about how a web worker actually looks in code, just to understand it briefly. Here we have a worker that I'm instantiating by creating a new worker and giving it a URL to point to. So this is the resource that will run within the worker. I'm going to create an input element that's on the main page. And when that element changes, so I get a callback when that element changes, I'm going to send a message over to the worker, a very carefully crafted message that that worker should understand because I also wrote the worker. And I can append the element to the body of the document, and now every single change event will send a message to that worker to be processed. But how do we get it back? Well, we need some more code. So now we've got the main thread, which will send a message over post message to the worker thread. The worker thread will process the information and send a post message back to the main thread, and then you'll be able to get the value. Whew. That's a lot of code and a lot of logic to figure out in order to do something really simple. I just want the worker to do some work for me and tell me when it's done. Now, I thought this talk was about AMP. Right? Like I've talked a lot about concurrency and not enough about AMP. That's absolutely correct. But there's a lot of background to get through to understand why we want the solution that we did. So we recently open sourced something called Worker DOM. It is the same DOM API that you know, that your frameworks know, except that it runs in a web worker. So previously workers had no access to the DOM. Now they do. This is specifically the key thing that we needed to make JavaScript in AMP a reality. So when Malta came up with the requirements for this project, they were really, really simple. He said, hey, Chris, make it so that React runs on a web worker. That was the entire list of the requirements. Unfortunately, we also realized quickly that we could be a little bit more abstract. So instead of just targeting React specifically or looking at its virtual DOM implementation, we could build something that all frameworks target, which is the actual DOM implementation. So Worker DOM makes the full DOM available within your worker. It means that you can run existing web applications or components from your web applications within a web worker. And most magically, it just works. Now, you might have noticed the one showing up a few times in here. There's good reason for that. We'll go over those. Those are the terms and conditions. Back to our example. We've got 10 milliseconds of processing happening for an event. 8 milliseconds for the browser to actually respond to those changes that we gave it to perform within our frame. And we've introduced jank in this example. It took us 18 milliseconds to respond to the event, but we also kept the main thread busy for that 18 milliseconds of time. In Worker DOM, we shift that work over to a different thread. So now the background thread that's running, that our web worker is running code on, is executing those tasks that previously were on the main thread. This means the main thread time is only 10 milliseconds. It still takes us 18 milliseconds to actually process and display the event or change the real DOM. But the main thread is only operating on 10 milliseconds of that 18 millisecond time. So we shouldn't drop frames during this time. Let's go through those limitations real quick. Some DOM API, some things from the DOM API are not yet implemented. It has been released, Worker DOM has been released in alpha form. We're working very hard on it, but there are many things that are just not done yet. A small number of the DOM APIs cannot be implemented, but we will provide alternatives. And a smaller number cannot be implemented, and we cannot provide alternatives for them. So what is unimplementable, but we have alternatives for? These are typically synchronous DOM APIs that access computed layout. Because the worker has no knowledge of what the layout of those DOM nodes are, it can't actually provide synchronous access to that data. It would need to ask the main thread for that data. So really great example is get bounding client rect or get computed style, which if you tried to implement in worker DOM would not exist because we don't know the size of those objects. But we can provide alternatives with get bounding client rect async, which returns a promise. And if you're using async await in your code, the delta in your code is literally await get bounding client rect async versus get bounding client rect. There is a benefit to this because many of these things cause layout to have to be recalculated. So if you're awaiting the response of it, you'll prohibit scenarios where you cause double layout within a single frame. What about the things that I can't promise we'll be able to implement? There are a few. So the main big one is synchronous methods on event, like prevent default and stop propagation. Because by the time the worker has received the event, it's impossible to prevent it from bubbling in the DOM, for instance. There is hope on the horizon. There is a spec proposal around transferable events that would allow events to be sent directly to a worker that may come to browsers soon, but we're not going to count on it. Until then, you may need to run these specific methods on the main thread. And this is the kind of thing that we still need to figure out how to make work well within AMP script. Let's talk a little bit about how this works. We don't need to get into all of the guts of how to use it in order to use it, but it is quite interesting. So we start with an AMP document. The AMP documents can contain the AMP runtime and AMP components, like AMP image, for instance. Now we'll add in a React component. So in this case, this React component was running on the main thread. If we did that, we would run into a problem because the React component can decide to do a virtual DOM diff at any time it would like. And when it does this, it may tie up the main thread for an indeterminate amount of time performing that operation. So what if we could take that specific thing and put it in a sandbox? That's exactly what we did. The worker is the sandbox from both a security and a performance perspective for that React component. Now that specific component can run within a worker thread, which is running worker DOM. You've got a document object that exists there, so the component is able to create elements on that document. And the way that this works is through a process where we upgrade a specific segment of the page. So we're saying to the worker, this element of the page, this AMP script element in particular, will be controlled by this worker and not by the main thread. After the code that runs in the worker thread has settled for the first time, we consider that a hydration event. This is the first time you're trying to draw that React component to the screen. And then after events occur, you can do mutation events on those elements. So let's go ahead and break down hydration. All right. In order to know how hydration works, we need to kind of step back and look at how the DOM actually works, how DOM parsing works. I've got an element here that's a section, HTML section element. It's got an attribute called source that provides the JavaScript that will power this specific element. Inside of this, I'm going to create an HTML div element. There's going to be a text element, followed by an HTML span element that itself has a child of a text element, and lastly, an input element. This structure we are going to use for several examples, so it's important to take a look at it real quick, kind of get it in your mind. And here we go. In order to be able to represent this thing in the hydration event, we need a single interface that will be able to express all of the different types of DOM nodes that exist. We call that a hydratable node. So it will contain the node type, the name of the node, in this case it's a div, with the index, which is a unique identifier for that node in both the background and the foreground thread, and whether or not this specific element has been transferred. So once an element has been transferred, the format that we can use is far more condensed. So being transferred is actually fairly important from a performance concern. There's some additional attributes here. We need to be able to say what other attributes exist on the DOM node. Does it have properties? What are the child nodes within it? The text content, if it's a text node itself, and a namespace. If you've ever used an SVG, you've used an HTML element with a namespace. So now we're able to represent that specific one node as a hydratable node. And you can see how we could take our tree structure and represent the rest of the nodes now as hydratable nodes. So that's what this looks like. We have a JSON object that is that specific node. In this case, I moved over to the section element. Apologize, I didn't update the slides. That section element has a single child node within it, and all of the indexes represent a unique identifier for both sides of the code. But something we learned, a very important discovery along the way, is that given the same complexity of a message, the size of the message actually has a material impact on how fast it transfers between threads. So let's make this smaller. Sounds like a simple task, and it actually works pretty well for this specific type of application. We're going to use something called a substitution cipher. It's a fancy term for a replacement. So we can say node type, node name, child nodes, index, transferred are actually just numerical indexes in a table. Now, we don't have to ship this table. We do this operation at build time. So the code that's outputted already does this for you. So now we were able to move that code over to look like the structure on the right. Next, we can apply the same technique over to false and true, which can be represented by their integer representations of 0 and 1. And lastly, we can do something that's a bit more dynamic. So we were transferring over here two strings, the word section and the word div. But we're going to send those specific strings over and over and over again as we send messages. So what we can do is create a pool of strings that we send and then reference the elements within that pool when we send those same strings multiple times. So section and div happen to be the first and the second and third element in our string pool, and we will continue to use those names with just their integer representations over time. So here's our finalized format, and as you can see, we've condensed it rather significantly. There's more opportunity for condensing it here, but the real magic here is that we're getting closer and closer to a typed array. The more close that we get to a typed array, the more performance benefits we can get out of using transferable objects within web workers. Here's an example of that full hydration message now. We have that node structure we talked about, and you can see there's that string pool that represents all of the possible strings and will continue to grow throughout the course of the application's lifecycle. All right, so that was hydration. We need some mutation. Static document would be quite boring. So what is mutation? When an event occurs that we need to respond to, we have to update the DOM. In this case, we're going to have an event listener that will toggle a few attributes and change some styles. How does this work? Well, we can use an API called Mutation Observer. Sorry for the white slide all of a sudden. The Mutation Observer is a specification that's been around for a while. Unfortunately, it doesn't have everything that we need. And since we were building our own DOM implementation, we also built a kind of super-powered version of Mutation Observer that gave us access to properties, not just attributes. So does this actually work? It does, and I'd like to do a few demos. Okay, so let's see. I can get this on screen. All right. We're running low on time, so we're going to do this meme. I'm going to start with the guy on the right or left, and then we're going to have the whole owl in about a minute and a half. All right. So if you check out the worker DOM repo, you can run npm run demo, and you'll get this exact page. You can try it out for yourself. Let's start with something simple. I've got a button here, and every time I click it, I'll get a new DOM node that says hello world. Now, that doesn't look like much of a demo, but what we've actually demonstrated here is hydration to put that element on screen to begin with. And every click event is sent to the worker. Then a mutation event occurs in the worker, and we are able to show the new DOM in the main thread. Let's keep going. Let's do some SVGs. So this demonstrates that namespaces are working correctly, which is actually a rather hard concept. You've seen a few times where it does not work. Let's move on to something a little bit more interactive. So here, this example is using the Preact web framework within the worker DOM context. So this is an AMP document that's able to power a Preact application running in the background. It's a rather simple demo, but this is an SVG and it represents kind of an interactive graphic. Say I was talking about an election that was happening. This could be a map of the election results, and as I move around, the code is actually powered by the background thread running a Preact application. And now it's time for the owl at the very end. This can't possibly be fast, right? Well, let's use a high volume write application. So dbmon is a very common application for this specific example. It represents a large number of DOM mutations happening fast, and a lot of them happening at once. We're able to maintain a solid 60 frames per second very easily. The only limit we have right now is around garbage collection. The actual transmission of messages is not high overhead and is working pretty well. Okay. Now I have to figure out how to get this back up here. Okay. When can I use this? Worker DOM is available today. It's available on GitHub. Go check it out. It's under the AMP project, like all of our open source repos are. And you're not going to be able to use it for much beyond experimentation at this point. It needs a few things to really get to rock solid status. So we need better performance tools for performance testing tools. This ensures that we don't have regressions in performance as we add capabilities. We need to finalize and implement that synchronous API replacement part I talked about earlier. We have an idea of how to do it. We just haven't implemented it. We also need to integrate more deeply with AMP state. So when you change AMP state somewhere in your application, the worker thread would know about it or be able to mutate it independently. And lastly, we really need deeper integration tests with popular frameworks. Since we're trying to make this work for all of the frameworks that we can, we need to make sure as they make changes that worker DOM continues to function correctly. If we have all these things in place, we feel pretty solid that this will actually work. And that's it.